In the last session, we discussed about the Kirchhoff's laws. There were two laws, the Kirchhoff's voltage law and the Kirchhoff's current law. We also stated that there are two categories of junctions in electric circuits. One is the voltage junction and the other is the current junctions. Now, these two laws along with these junctions, the voltage junction being called the loop and the current junction being called the node, will be essential for doing any analysis of the circuit. So, today we shall discuss about how we go about modeling circuits such that it will result in a mathematical representation of the circuit. So, this mathematical representation of the circuit will then be used for analyzing the circuit and knowing more about the circuit. So, today's topic is on modeling of circuits. Consider a circuit, a simple circuit with a source, a resistance, let's say capacitance, all of them connected in series in this manner. The source, you have Vi, there is a resistance R and capacitance C. The source has the voltage, the arrow direction in that as shown here, the voltage across the resistance and the voltage across the capacitance shown like this. So, by the Kirchhoff's voltage law, because this is a junction, and what junction is it? This is a voltage junction. Or a loop. And what does Kirchhoff's voltage law state? The Kirchhoff's voltage law or the KVL states that the algebraic sum of all the voltages in this loop must be 0. So, therefore, Vi is equal to Vr, which is the voltage across the resistance, plus Vc, which is the voltage across the capacitance. So, this is the equation for the circuit, but however, this equation does not fully describe the circuit which is having the components like the resistance and the capacitance. We need to have much more detail to understand the circuit and analyze the circuit. So, the question arises, how do we dynamically describe the circuit? So, how do we describe the dynamic behavior of circuits? In this session, we are going to take one approach. There are many approaches, of course, but we will take one approach which is kind of universal in its approach, whether it be electric circuits or whether it be the magnetic domain or the mechanical domain. However, we are restricting ourselves to the electric domain, the state space approach. It is called the state space approach. So, throughout this session and also in the future classes, we are going to use only the state space approach to mathematically represent the circuits and then thereby afterwards use it for analysis. So, in the state space approach, the behavior of the system at any given instant is fully defined by two main variables. One is the input. You have two keys, one is the input and the other the state variables. The input is the source voltage or the source current, as the case may be in any particular given circuit, and the state variables. You may not have come across the state variables. Let me give you an idea about the state variables before we proceed further in this state space approach. So, if we have the knowledge about the input variable value and the state variable values, then the whole system can be defined. So, let x be the state variable and let u be the input variable. Then the state equation can be written as x dot equals a x plus b u. And there is one more equation, the output equation, which is written as y is equal to c x plus d u. This is the standard form of representing all systems in the state space domain, and this is called the state equation. I will come back to the state equations again. Let us first have a look at what state variable is. The state variable. What can become a state variable? We have mentioned earlier that the inductance, capacitance, and probably in other domains the inertias, they are all energy storing elements. The variable associated with the energy storing elements, for example, in the case of the inductor, the current is the variable that is associated with the energy storage, because it is kinetic energy that is getting stored in the inductor. So, the current becomes a candidate for being considered as a state variable. And the case of the capacitance, which is a potential energy storing element, the voltage can be a candidate for being considered as a state variable. So, in short, we can say the variable associated with energy storing components can be considered as state variable. But if you see in the case of the signal processing circuits, where you use lot of memories, RAMs, and in microcontroller circuits where there are a lot of memories involved, there also there is some storage, but the storage there is information. So, the variables associated with information storage also can be considered as state variables. So, not only energy storing, even variables associated with information storage. Now, we can state from these two that any variable that is associated with a component having memory can be considered as state variable, and that would be the most general statement. Any variable that is associated with a component having memory, then that variable is a candidate for being considered as a state variable. For example, let me take the case of the inductor. The inductor L. So, in the inductor, the energy is stored by virtue of the kinetic energy, by virtue of the flow of the current. So, and it is given by half L I square, which we saw in the one of the earlier sessions. This current here is the means by which the energy is getting stored, and this current is a candidate for state variable, and that can be a state variable. Or if you consider a capacitance C, the energy here is stored by virtue of the potential across the capacitance, which is half C V square, and this voltage across the capacitance can be considered as state variable. Or in any other domain for that matter, if you take an inertial element J, which is being rotated by a shaft of a motor, J also stores the kinetic energy of the angular rotation, and the energy is given by half J omega square, and therefore, the omega, the angular speed of rotation, is a candidate for being considered as state variable. And also in the information domain, the variables stored in the memories, in the RAM memories, can also be considered as state variables in the signal, the information domain. So, now that being the case, that we consider the variables associated with components which store energy or store information, or in other words, components that have memory or history, then such variables can well be considered for a state variable to be applied in the analysis of the circuits or to develop the mathematical representation. So, now coming to the circuit, consider the circuit that we wrote quite some time ago, that we have a source, we have a resistance and a capacitance. All these are connected in series, all these share the same current, and they are all in a loop, and therefore this is a voltage junction. And if it is a voltage junction, what should agree? The KVL should be obeyed. The Kirchhoff's voltage law should be obeyed for this loop. So here you have the R, you have the C, and you have the source, which is Vi. Now there is a voltage which is considered this direction. There is a voltage across R which is this direction. There is a voltage across C which is in this direction. So now the question, how does one get the mathematical representation of this circuit? How does one obtain the mathematical model of the circuit? So let us go step by step. Step 1. First, after having the circuit and mark this one, identify the energy storing or the memory components. Identify the energy storing components. After having identified the energy storing components, in this case for this circuit there is only one energy storing component, which is the capacitor here. The step 2 would be to identify the state variable. So in this circuit there is only one energy storing component, therefore there has to be only one state variable, and as it is a capacitor, the state variable for the capacitor is Vc, because the energy is stored by virtue of the potential across the capacitance, and therefore we write down the state variable for the capacitance, which is the voltage across the capacitor Vc. Now having done this, that is having identified the energy storing components and having identified the state variable, put down or write down the state variable at the corresponding or appropriate place in the circuit. The circuit should contain only the input variables, the state variables, and the parameter variables like the R and C's. And the whole equation should be constructed only with these variables. Now in this case, the whole equation should be constructed with Vi, the Vc the state variable, R the parameter, C the parameter of the circuit. Now step 3. Consider the dynamic equation at the energy storing components. One by one. Order immaterial. What it means is, we consider the dynamic equation at the energy storing component one by one, and if a particular circuit contains more than one energy storing component, you can do it in any order. So, in this case there is only one energy storing component, which is the capacitance. So, we need to look at the equation of the capacitors alone. So, the equation of the capacitance is C dVc by dt is equal to the current through the capacitance. So, if we look at the circuit here, we see C dVc by dt equal to the current through the capacitance. And what is the current through the capacitance? It is the same as the current through the resistance, which is the same as the current through the Vi, because this is a loop. So, what is the current through the resistance? Vi minus Vc divided by R, and that is the current that is flowing through the capacitance. So, therefore, which is equal to Vi minus Vc by whole by R. Note that in this equation only the input and the state variables are used apart from the parameters. So, now this equation can be rewritten in the following form: dVc by dt equals minus Vc by Rc plus Vi by Rc. This is now in the standard form. So, if you look at this, this is dVc by dt, which is Vc dot, okay, equals. Now, this can be written as minus 1 by Rc into Vc plus 1 by Rc into Vi. Now, see that, compare this with the standard form, which is x dot, which is equal to A x plus B u. There is a one-to-one correspondence between these two. Vc dot, Vc is the state variable, which is x. A is the parameter matrix, the system parameter matrix. This is the system parameter matrix. B is the input matrix. And if there are more than one state variable, this is a vector, x is a vector. If there is more than one input variable, then this is also a vector u. Now, there is one more equation that you have to write to complete the state equation, which is y, the output is given by 1 into Vc plus 0 into Vi. Is the general form, which comes in the form of y. Compare this with the general form of the output equation, y equals C x plus d u. Again, the equivalence between these two. This is the state vector and this is the output matrix. C is the output matrix, D is the feed forward matrix, the input that comes directly to the output without going through the dynamics of the system. Now, these two equations together form the state equations. So, therefore, Vc dot equals minus 1 by RC into VC plus 1 by RC into VI, that is one equation. And here this gives you the dynamic information, and Y, which is 1 into VC in this case, because the output is same as VC, plus 0 into VI. So, these two equations together are called the state equation for that circuit. This is the dynamic equation, which is a first order differential equation, and this is the output equation here. So, the dynamic equation, which is the first order differential equation, and the output equation together describes the system completely, and we see that this equation, to describe it completely, needs just the input variable and the state variable, and the state variable is nothing but the variable associated with the energy storing component of the particular circuit. Now, take another example. With slight modification. Let me put the inductor instead of a capacitance. So, we have a resistance and an inductor. This is an RL circuit. The previous circuit was an RC circuit. So, we have an RL circuit VI and we have the source having a direction like this. We have a passive component and another passive component. So, in this case, again going step by step, what is the first step? The first step is to identify the component which stores energy, and in this case it is the inductor L. The second step is to identify the state variable for this energy storing component, and for L the energy is stored as half Li square by virtue of the flow of the current, and therefore IL. Therefore, IL is the state variable. IL is the state variable. This is the state variable. And in the circuit, you just have those variables only that are essential for making the equation, which is the input variable Vi, the state variable IL, and the parameters of the circuit R and L. You need not mention any other variable other than this. These variables are sufficient to completely describe the circuit. And then we consider the equation, third step, of the dynamic elements, and in this case the dynamic element or the energy storing element is the inductor. So, you consider the equation L di by dt is equal to VL, or the voltage across the inductor. I will mention it as voltage across L. So, applying this third condition, we have L dIL by dt equals. Now, what is the voltage across the inductor? One end is ground here, the circuit ground. The other end here is Vi minus the voltage across R. And we know the state variable IL is flowing through whole of the circuit, and therefore, the drop across this is nothing but IL into R. So, Vi minus IL into R is the voltage across the inductance. Vi minus IL into R is the voltage across the inductance. So, you see again the whole dynamic equation is in terms of only the state variable and the input variable. So, putting it in the standard form, dIL by dt is equal to, where IL is the state variable, minus R by L into IL, the state variable, plus 1 by L into the input variable. And then the output variable for us, let us say, is IL. So, if it is IL, or if it is across the resistance, let us say. So, let us say the output is VR, just for a change. This is what we want. VR. So, the output VR is equal to R into IL plus 0 into Vi. So, the C matrix is R in this case. So, these two together fully describe the circuit, and that is the state equation for this circuit. You see, it is so simple. Actually, whatever be the complexity of the circuit, you just have to follow these 3 steps. That is, step 1, identify the energy storing elements. Step 2, identify the state variables corresponding or associated with these energy storing elements. Step 3, with no particular order, starting at any particular energy storing element, the equation describing its dynamic behavior can be put down, and then followed by the equation describing the dynamic behavior of any other, all other energy storing elements in the circuit. So, that is the method that we will be following. So, let us just take a bit more complex, actually simple, but just a bit more complex compared to the earlier RL and RC circuit that we have been seeing. The third example is like this. So, let us have an R, let us have an L, let us have a node with a capacitance C, and let us have another resistance R across C as shown here. So, this is the input Vi. This is one resistor R1 which is in series with an inductor L. There is a capacitance, and there is another resistance R2 which is across C. So, let us say this is the circuit that you want to analyze. So, which means that you have to have a mathematical representation of this circuit, the complete dynamic behavior of this circuit. Notice here that there is a loop here, that is, there is a voltage of the source represented like that. We have the voltage across R represented like this, the voltage across the inductor, the voltage across the capacitance. There is a loop here, and there is a node here. So, what does it state? The node is a current junction. It states that all the currents, the algebraic sum of all the currents of these branches should add up to 0. The loop states that the algebraic sum of all the voltages in this loop should add up to 0. Okay, that is this is the KVL and this is the KCL. Okay, we make use of these two laws, of course. Now, step 1, identify the energy storage elements. In this circuit, there are two energy storage elements. There is an L and a C. So, we have L and C. Second step, identify the state variables associated with these energy storage elements. So, for L, we shall call it as IL. The current through the inductor is a state variable, and for C, we shall call it as Vc. The voltage across C is a state variable. Now, put these state variables or mark these state variables in the circuit. So, in the case of the inductor state variable, this is IL, and in the case of the capacitance state variable, the Vc, the voltage across the capacitance. Okay. Now, let me erase these things so that it will not disturb the overall. Yeah. So, now it is required to have a look at the output voltage V naught. Note that the V naught can be expressed in terms of the state variables. This is the output, the Y that we use to describe, which is in this case same as Vc. But on the circuit, we just keep only those variables which we need to form the equation, which is the input variable Vi, the state variable Vc, state variable IL, parameters of the circuits R1, L, C and R2. Okay. These are the only variables that need to be written down on the circuit, and the whole dynamic behavior of the circuit should be formulated with just these variables, nothing more, nothing less. So, what is the step 3? One by one, we take the equation describing the dynamic behavior of the energy storing elements. So, we have two energy storing elements L and C. So, first we consider the dynamic behavior of L, and then consider the equation defining the dynamic behavior of C, and then write down the expressions only in terms of these variables that you see on the circuit. So, first the inductance equation given by L d IL by dt should be equal to the voltage across the inductance. Now, the voltage across the inductance should be expressed only in terms of these variables. Now, what is the voltage across R1 here? The voltage across R1 can be expressed in terms of the state variable. The current IL is flowing through R1, and therefore, it has to be IL R1. So, now looking at the graph circuit here and applying KVL, L di by dt is equal to Vi minus IL R1 will be the voltage of this node with respect to ground, and the voltage of this node with respect to ground minus Vc. So, looking at the circuit, we see that this is the dynamic behavior that we have obtained by considering the equation revolving around the inductor element, and you see that the whole equation is formulated only with the input, the state variables alone. So, let us consider the second element, and the second element in this case is the capacitor C. C dV C by dt equals the current through the capacitance. And now what is the current through the capacitance? There is a current flowing from the inductor IL here, there is a current through the capacitance here, and there is a current which flows through R2, and by KCL it is known that the algebraic sum of this current and this current and this current should add up to 0. So, here we have IL, and what is this current here? The one which flows through R2. Can it be expressed in terms of state variable? We know that the node voltage here is Vc. So, Vc by R2 is the current which is flowing through R2 here. So, therefore, the current flowing through C is IL minus Vc by R2, as simple as that. So, these two equations, there are two dynamic components or the energy storing components, and therefore, there are two equations, and these two equations totally describe the dynamic behavior of this circuit. However, we need to put it in the standard form, express it in the standard form. So, let us define X. Now, let me go to the next page. Let me rewrite these two equations. L dIL by dt equals Vi minus IL R1 minus Vc, and the other equation C dVc by dt equals IL minus Vc by R2. Now, these are the two equations. Now, we need to remove L from here. So, I will remove L from here and divide everything throughout by L, and then I remove C from here and divide everything throughout by C. So, that now we have the state vector. And we can now rewrite this as IL dot Vc dot enclosed in matrix. So, let us put it in the matrix form, it is very, very elegant. And let us write the A matrix also in the matrix form. We see this is the state vector X plus we have to write the input scaling matrix, and there is of course only one input, which is Vi. So, IL dot equals IL is multiplied by minus R1 by C, R1 by L, R1 by L, and minus 1 by L into Vc, minus 1 by L into Vc. Then for the second equation, dVc by dt, Vc dot equals IL into 1 by C, IL into 1 by C, and Vc into 1 by R2 minus 1 by R2 C into Vc, plus here you have 1 by L into Vi, there is no Vi term here, that is 0. So, this is one equation which describes the dynamic behavior of the circuit, and then we need to get the output equation, which is V naught, which is same as V c, and therefore, we have 0 1, you have I L V c plus 0 into V I. So, now this is your state equation, which completely describes the circuit as shown in this figure. So, you see here, this is the derivative of the state vector x dot, and this is the state vector x, and this is of course the input vector. Of course, in this case this is a single element, and therefore, it is a 1 by 1 matrix, and here is the input matrix, and this is the matrix which describes the circuit in terms of the circuit parameters R's and C's and all those things. And here you see this is the output Y, the C matrix here, because in this case V naught is same as V c, is the C matrix. This of course again is the X matrix. The D matrix is 0 because V I is not directly passed on to the output, and this is U. And you see that there is a one-to-one correspondence between the general standard representation of the state equation and this here. So, this is a complete mathematical representation of that particular circuit. So, all circuits can be represented in this form. Now, at this point, I would like to state that we have two important laws, which is the Kirchhoff's voltage law, which we have been applying for all the loops here, and the second is the Kirchhoff's current law, which is being applied for all the nodes. All the circuits, all electric circuits are composed of alternately these loops and nodes. So, you have the voltage junction which alternates with the current junction and so on. So, this happens in even the most complex circuits. And to obtain the mathematical representation, we just have a very simple 3-step process. First step is to identify all the energy storing components. After having identified the energy storing components, identify the state variables. It is very simple. In the case of electric circuits, when you restrict to electric circuits, which is, if it is an inductor, the inductor current is a state variable, and if it is the capacitance, the voltage across the capacitance is a state variable. So, after having identified all the inductor currents and the state variables, mark them on the circuit. And if it is a loop like we see here, let us say, just check if all the voltages across the components have been identified. Like for example, in the case of the resistance here, it was not identified, but express it, it will always be expressible in terms of a state variable. So, therefore, try to identify that state variable which will decide the voltage and so on. And as R is in series with L, the state variable IL is used for finding the voltage across R. So, IL R1 is the voltage across that one. So, all the elements, the voltages across them have been identified. Now, apply KVL for this loop. You will get the dynamic equation, one dynamic equation corresponding to that particular energy storing element. Then choose the other energy storing element, in this case it is the C, and here as it is connected to the node, you apply the KCL, KCL, because C dVc by dt is going to be equal to the currents through the capacitance. So, for the inductor you are applying the KVL to get the voltage across it, and for the capacitance you are applying the KCL to get the current through the inductor, to get the current through the capacitance. With these two, you have defined the dynamic behavior of the entire circuit just only in terms of these energy storing elements and the input elements and the parameters of the circuit. And this process is valid for whatever may be the complexity of the circuit and whatever may be the domain, whether it be in the electrical domain or it be in the mechanical domain, or it be in the hydraulic domain, or it be in the magnetic domain, so on and so forth. Just one point of caution that you need to be careful about is what happens if I have two inductors in series or two capacitors in series. For example, in a case like this, let us say we had a resistance, an inductor followed by a capacitance and a resistance like. So, here you have, let us say, R1, L1, L2, C, R2 and an input source Vi. You will see that there are three energy storing elements. Apparently, it looks like there are three energy storing elements, L1, L2 and C, and therefore, there should be three state variables, but it is not actually so. This L1 and L2 are actually one single inductance. It can be considered as one single inductance L equivalent, or either one of two, or either the L1 inductor or the L2 inductor can be considered as the energy storing element and the corresponding variable can be taken as the state variable, which means in this case, as they are all coming in a loop, the current through L1 and the current through L2 are same. So, only one of them can act as a state variable. Likewise, you can have a similar problem. So, which means that there will be one single IL, either by taking it as equivalent inductance or taking it as the state variable corresponding to L2 or taking it as the state variable corresponding to L1, and the other state variable will be Vc. The other problem could be something like this. I have an R, I have an L, I have a C, another C, and let us say a resistance. This also could lead to a conflict in making your decision of what should be the number of state variables. So, I have a state variable here IL, we have Vi. Now, either we combine C1 and C2 and make it a C equivalent and have one common state variable Vc for that, or associate Vc with either C1 or associate Vc with C2, any one of them. So, there will be only two state variables, a Vc and an IL. There is one more case which you may land up with, and that is a network something like this. Let us say you have an R, you have an L, and you have another inductance there, you have an R and something like this. So, here we would be considering, let us say this is IL1 and let us say this is considered as IL2. So, once this becomes the state variable, this current here through the third inductor is automatically determined by the Kirchhoff's current law here, and this is most fundamental. There should not be any accumulation of current here. So, by Kirchhoff's current law, this is IL1 plus IL2, and therefore, this is not a state variable. There is only two state variables, even though it apparently seems that there are three energy storing elements. Only any two of them here would have the memory, and any two of them, either you can say IL1 and IL2 are state variables, or IL1 and the current through the middle arm is a state variable, the other one being determined by KCL, or it could be IL2 and the middle arm being the state variables and the current through the inductor 1 L1 being determined by KCL. Okay. These are some of the special cases that you should be aware of and be careful about when you are doing the decision on the state variables. Otherwise, the process remains the same, and for the majority of the cases, except for these special cases, you will find the process that we stated or that we discussed today, that is the step 1, step 2, step 3 is valid for whatever may be the domains. Okay. With this, we stop the discussion here about obtaining the mathematical representation of the circuits. Thank you.